What's happening, everyone? My name is David, and this is Tippy Bits. And today we're going to be talking about, do you need semantic search? What is semantic search? Why would anyone want to use it? We're going to be implementing this today in OpenSearch because that's my tool of choice. However, there are plenty of other places you can do this, such as Weaviate, Vespa, etc. So let's start really quick with what semantic search is and what OpenSearch does out of the box. So out of the box, OpenSearch is a lexical document store. And that means it takes and it has documents like these ones here. They have IDs, and it will take your search and it will try and match the exact words from your search to the words of the documents. Like this. Here we've got two documents where we have Senna was a beloved race car driver, and Tiger Woods loves his Titleist 975D golf driver. So, in a lexical search scenario, we would say, hey, look, we're looking for supercar driver. Well, the only word from here that is in either of these documents is driver. So it's going to say, okay, driver's in this document, driver's in this document. We return both documents. But if you'll notice, we know that race car and a supercar are similar. But lexical document searches don't know that. Now, they can know that. You can build out synonyms and all of that. However, then it becomes really brittle because you constantly are updating these synonym lists and trying to remember all the different variations of like supercar, race car, hypercar that might be synonymous. So this is kind of why semantic search came to be. We needed some way to understand what is being said and be able to dynamically map that to what documents we have. So synonyms is kind of one use case. Another thing is you might write a long phrase like, I want to know who is the best supercar driver of all times. And here this could say, oh, Senna was beloved. Okay, so that is a match for that query. So how does semantic search do this? I'm so glad you asked. We're going to first talk about, what is semantic search and how it relates to vector search, because you'll probably hear those used very often in the same phrase, right? Like someone will say, oh yeah, semantic search, vector search, and you're like, what? What are they the same? Are they different? So semantic embedding models are models that have been trained on sentences. So you'll have like one sentence that says one thing, one sentence that says another thing, and a person generally has gone through and said, these sentences are very similar or dissimilar. Then these semantic models produce what's called a vector. So out of the semantic model, you'll put in your sentence. It'll say, hey, this is a array of floating point numbers that represents that sentence. Then those vectors can all be used to compare different sentences or documents against each other. This is the same way that image embedding models work. They'll produce a vector of arrays, and that vector representation then can be compared to other vectors. So semantic embedding or semantic search is an implementation of vector search, right? It produces vectors specifically used for comparing documents. So let's take a look at how this works under the hood. Here we've got a couple different, we'll say sentences. These are groups of words really, but you would take and ingest your document. So we have race car driver is maybe a document that gets ingested into a three-dimension floating point array. And this is very important. We'll talk about that more in just a second. We've got golf driver that gets embedded and created into a vector. Here we go. We've got round of golf. That also gets put into an embedding. So embeddings, no matter how long the input is, always have a fixed length. So here, these vectors are all 3 dimensions because they have 3 floating point numbers that are used to represent the original documents. No embedding models really produce three dimensions. Normally it's anywhere from, a couple hundred dimensions to many thousand dimensions, depending on the model. And the model that you choose also affects performance. It affects a lot of other things. So here's what this actually looks like. So these vector representations can then be plotted and compared against each other. So here we have, let's say, race car driver. So this gets plotted here at 0.55 for the first two, and then 0.12, we're going to just say that's the angle. That really doesn't matter for this. Then we've plotted golf driver. That is at 0.3, 0.5. So come over 0.3, up 0.5, and then round of golf is at 0.3, 0.02, which I didn't put 0.02, but you can just imagine it there. So if we're looking at this, we can say that, hey, these all kind of share attributes. So like driver, for example, lives on the 0.5 dimension on the y-axis. Golf lives on the 0.3 dimension. So this is kind of a way that we can say, hey, look, maybe these share attributes because they share a certain dimension. So anything maybe falling close to 0.3 on the x might be close to golf. Now this is a little bit of a strained comparison, and the reason is dimensionality doesn't work out quite like this. You can't really tie a single dimension down to an attribute like golf. These models produce huge dimensional arrays, so it's more like, hey, 0.03, 0.2, 0.7, 0.45, all are like golf-like, we'll say. So let's go and take a look, and we'll go through that same search we did earlier. Now we have supercar driver. So if you want to do a search for supercar driver, the first thing you have to do is, again, using that semantic embedding model, we create a vector for that search. That vector here is 0.46, 0.5, 0.01, and then we plot it against all the other documents. And here we can see, okay, 0.46 is going to be right here, 0.5, okay, 0.5 on this dimension, 0.01, maybe it's 0.1, but whatever. We're not going to worry about that too much. But the point is, we've taken and we've plotted this, and we can say that supercar driver is really close to race car driver. So this is how semantic search works. We're taking these models, producing embeddings, and then comparing them to the other embeddings we have. Now we could say, golf driver maybe is a little bit close, but a round of golf is not very close. So with that, let's go ahead and actually implement this. Let's implement this in OpenSearch. So we've talked about a couple different phases. The first is we have to ingest or have a model that we can use to embed. Then we need to ingest documents through that model. Then we need to have a way to search. So we're going to go here, and one point that I'm going to show quickly is if you have not set up your Docker before, you're going to want to go in through settings up in the top right, resources, which also I'm aware this looks different on Windows, advanced, and you're going to want to increase the memory that's used for Docker Desktop. I think Windows users, it might automatically just, I don't know how it does memory, but I remember it was different. But you're going to want more than 4 gigabytes of memory. So, or 4 gigabytes, we'll say, at the minimum for running OpenSearch. So now that we've got that, I'm going to figure out where my other tab is. Code here. Oops, nope. We're going to go here first. So I have this little gist, and this gist basically will help us download a shell script that will set us up with an OpenSearch instance using Docker. So we're going to go here into my Visual Studio Code. I'm going to just paste this little shell script here, this curl command, and that's going to go ahead. We'll take a look at that. That has downloaded our shell script, and all this really does is creates like an env file that has a password for OpenSearch and creates a Docker Compose file. So we're going to make this file execute by doing executable, which means chmod plus execute OpenSearch bootstrap. This is going to make it so that we can run our shell script, so chmod plus x, and then we will actually run it, which // will run that. We can see it's created two different things up here. The first is, let's do this. The first is a Docker Compose file that spins up OpenSearch with the latest version because we're not passing it any parameters. It is gonna get the OpenSearch password here and then as an environment variable, and that's going to be scooped from our end file, which this is an automatically generated password. So, sorry, you guys can't steal my OpenSearch instance with this because this was generated with OpenSSL, which you can see if you come into here. Here we go. Yep, OpenSSL creates a random password for us. And with that, let's go ahead and start this up. So to do this, we're going to do docker compose up tech d or -d, which is going to run our Docker Compose containers detached, which means it's not going to be just outputting everything into our shell. Now mine's created really fast because I've done this before and it already had those OpenSearch containers cached locally, but yours might take a little bit longer. Now with that, we're going to go ahead and we're going to go and I'm going to show you this first. This is a markdown file that has all of the commands we'll be running. So you can go and clone this down as well and then copy and paste this into your local OpenSearch instance. I said local search because I'm looking at localhost. So here, we're going to need our new password here. I'm going to copy that from our end file. Oops. Paste that in. And we'll go ahead and log in. And again, this might take a minute as OpenSearch is spinning up in the background. Next, we're going to go to DevTools. And as you can see, I already have all of this code from here already in OpenSearch. So I'm going to go ahead and get started. If you'd like to pause and wait while you're waiting for your containers to download, please do. First thing we're going to do is put in our cluster settings. No settings to update. Right, okay. So this is one funny thing. OpenSearch, the managed service on Amazon, actually does these settings a little bit different. So this is how you have to do it on the managed service because it doesn't support the mode that I'm going to show you now. So persistent plugins ML commons. On the OpenSearch managed service with Amazon, you're going to have to do persistent.plugins.mlcommons.allow registering model via URL. It's very, very confusing, but we're going to go ahead and do that. Awesome. It's been acknowledged. Next, we're going to create a model group. This is just an access control mechanism. So we're going to go ahead and register that, copy the model group ID, and we'll paste it here so that we can remember it for later. This is just saying, hey, anyone with access to our tenant, which we are on the private admin tenant, will be able to use this model group. I'm going to go ahead and copy that in here and paste that here because this is the first place that model group is used. Oops. There we go. Delete, paste. There we go. So now what we're going to do is register a model. And I'm going to show you this really quick because this is really important. There are a lot of ways that you can get models. There are some custom models that you can use. So these are PyTorch models. OpenSearch provides pre-trained models for sentence embedding, and they're all found here. And the nice thing about these is you know they are certified to work with OpenSearch. So here we're going to go ahead and we're going to, we are using transformers, MS Marco, Distilbert, base, TOS, B. Just because that's the one I'm using for the demo. There's no particular reason. Different models will have different performance, but we're not going to talk about that here. And also another point to remember is when you pick this, you're going to want to also remember the dimension space, which we'll talk about later. So I'm going to go ahead and do this. Registering this model is actually just downloading it locally into the OpenSearch cluster. So it's available for us to run. So I'm going to paste this here. This is a task ID. We're going to also paste it here. And this just has us, there we go. There we go. We can see that this task has completed. This is the model ID that was created. So it's downloaded this model. Now we actually have to go and deploy the model, which is to load it into memory and make it usable. Also, I'll note there is a parameter here for auto redeploy so that every time your cluster restarts, you don't have to manually deploy this. I've not set that here, but I will have that actually set in the template. So here we go. We've now created a task to deploy that model because it takes a little bit of time. Many of these steps are kind of asynchronous as you're waiting for different things to happen. So here we've got our new task ID. We're going to go ahead and go plugins ML tasks to check and see if that's deployed. Huzzah, it's completed. Now, if you ever lose track of your task ID, which you are bound to do, I have, or your model ID or whatever, most of these are searchable. So you can do plugins _ML tasks _search, and you can just execute a normal search in here. So that last one was of type deploy model. So we're going to go ahead and we're going to look for our tasks of type deploy model. And here we can see we've only deployed one model here, and that was the output model ID. Now I'm going to go back from earlier and I'm going to copy that model ID again. And we're going to test this. So this is an important step. Like when you're creating these connectors, when you are creating these models, you want to make sure that they're actually installed and working correctly. So here we go. We've got, this should get embedded. I'm going to send it. And this is going to send this through the model's predict interface, create a text embedding for this text. And here we can see there is our 768 dimension floating point array of what this 4-word sentence produced. And this is actually one of the challenges. When you have smaller documents like this, the model is always going to output the same number of dimensions. So you are always going to get a 768 dimension array. And sometimes that's good because that gives you a lot of consistency. So if you have much larger documents, you can actually store them in a much smaller space. However, I will say if you use documents that are too large for the model, so maybe you put an entire book through a machine learning model that produces 768 dimensions, you're not going to be able to represent that entire book well in that compressed space. So that is something to be wary of. In that example, I would chunk my book down into paragraphs or something like that, and then retrieve the paragraphs, and then the book with the most number of paragraphs returned would then be what I would return as the book. So we're going to go here. We've got our model ID again, and this is an ingestion pipeline. So we talked about earlier, every time that we send documents into our index, we don't want to have to create these sentence embeddings manually, right? We want it to happen automatically. So what we're going to do is create an ingestion pipeline. And what this ingestion pipeline does is says, hey, anytime something comes in and it has a content field, we're going to embed that content field and store it in the content embedding field. And I've arbitrarily named this our embedding ingest pipeline. You can name that whatever you wanted. So we're going to go ahead and create that. Great. That's done now. But this is just sitting in outer space. So this isn't attached to anything. This isn't going to automatically embed anything until we attach it to an index. So I'll show you how we do that in just a second. The other part of this is we're actually going to be doing hybrid search in this demo. So I'm going to go ahead and create a search pipeline. And this basically says every time we are going to run a search, we're going to run it twice. We're going to do once with the lexical search and once with the vector search. And then we're going to combine the results. So that way, if lexical search returns the best results, maybe there are exact keyword matches, and that's a good thing, we'll boost the lexical result. Otherwise, if lexical isn't returning anything, vectors should return something, and then we'll use the vectors. So again, I've just arbitrarily named this the hybrid search pipeline, And there are a lot of different ways you can combine those results. I'm using arithmetic mean and then min-max for normalizing, but there are all sorts of settings that you guys can go find if you want. Now, the last configuration piece, we'll say, this is the last configuration piece, is we have to actually create our index. So I'm going to create the documents index. I'm going to say, hey, documents index, as things are ingested, use the embedding ingest pipeline, and then use the hybrid search pipeline. Then here is where we're going to get into some of those model details that we were using earlier. So we said this model has 768 dimensions that we found here from this. And then we're going to be using inner product, which I think is just a reskin of dot product, hierarchical navigable small world graphs, and NMSlib. Now these are all choices. Inner product is something that you probably need to use for this model. This is basically how those vectors are compared. And each model is going to have a different way that it prefers to be compared, or prefers to have its vectors compared. That's because that's what it was trained on. This is not, I believe this might be in our model config, but this is something you're just going to have to do a little digging on. Same with NMSlib. OpenSearch supports 3 vector stores out of the box. It's Lucine's vector store, NMSlib, and FICE. These are all different like storage and retrieval technologies for these vectors. And they all have kind of different features. For example, FICE does much better with filtering. They use memory a little bit differently. So I'm not going to dive too much more into that. We're going to use NMSlib because it's a great default out of the box. But that is just something to know. And we are creating our content field here, and it is of type text. So we're going to go ahead and create our index now. Huzzah, it's been created. Now comes the fun part. We get to actually upload documents. So for those who haven't seen OpenSearch's bulk endpoint, it is going to be the verb that we want to do, which is we are trying to index a document with ID, and then it is the actual document. And bulk expects new line delimited JSON, so we're going to go ahead and send this through. Great. There were no errors, which this is an important thing to note. Bulk will always return 200 so long as you can access the cluster. It will return errors in a different part of the array. And that is because sometimes some items were successful, some items were unsuccessful, but we don't want to fail the successful items. So it will return 200 so long as it was able to connect. But if there were errors, it will tell you about it. And sometimes errors can be from things like, you know, maybe earlier today I had embedding with 3Ds in here. And it's like embedding pipeline doesn't exist. All right. Now we've got several different documents in our index, and we can actually do a search. And I mentioned before that we are going to be doing a lexical search alongside a vector search. So here's what that looks like. We're saying we're doing a hybrid search, and our first query, which is the lexical query, is we're doing a match where the content field is equal to sports automobile. And again, this is content field, so I'm looking in the text fields here. So it's going to be looking for the word sports and automobile. If we look, the word sports and automobile appear in none of these documents. So if I was only doing lexical search in this instance, no documents would be returned. But we also have our neural search here. And our neural search says, hey, from the content embedding field, let's look for the query text sports automobile. And hopefully I have that model ID saved on my clipboard. Otherwise, I'm going to be going back up through my history. Yes, I do. And now this is going to do that vector search where it's going to use our model to embed the word sports automobile and then to search against the index and say, hey, in the content embedding field, does this vector match any of those other vectors? So we can go ahead and run this. And here we say, oh, look, there was once a race car driver that was super fast. That matched sports automobile. Some may say that supercar drivers don't really mind risk. that was a match, and that was, we'll say 20%. So this is a 0 to 1 scale. So you could say this is like a 70% match. This is a 20% match. And then actually, the interesting thing is it actually returned our golf driver document as well. But that was 0.000, well, it would say 0.07% match, which is a very low match. I mean, in most search engines, you'd cap out at maybe 50%. You'd filter out anything below that. So let's talk about why was golf driver returned for sports automobile. We know race car driver, right? Race car, sports automobile. Well, the reason that race car driver was likely returned, and again, we don't know exactly because embeddings are very hard to understand, but we know racing is a sport, and it's a sport involving automobiles or cars. So sports automobile matches the sentiment of racing and driving. One of the interesting things is supercars are not a sport. So it only matched the automobile portion of this vector. Now, the other interesting thing is you might look at this and say, hey, I bet driver matched here, and that's why it returned, because driver, automobile, those are kind of similar. My theory for this document is actually because golf is a sport, and we said sports. So it said, hey, sports, golf is a sport. It's not really the same as a racing sport or an automobile sport. So that's why it got returned with such a small accuracy. And this is one of the challenges of this is we have no way right now to say exactly why. However, there are models that allow you to attribute, but that is not available at this point in OpenSearch. If you want to, Joe Christian from Vespa has a really, really great demo about this, and I'll try and link it in the description below. But this is our semantic search. So why wouldn't you use semantic search then? This seems awesome. And there are kind of two real reasons. The first is sometimes your business uses language that just isn't in the training set for these semantic models. So say, for example, you're in some very niche legal field, right? You might use wording that just the models weren't even trained on. And as a result, they're not going to be able to find them super well. So a great example of this is SSFO is simple schema for observability in OpenSearch. And a model wouldn't know that because simple schema for observability is so niche and so specific to just OpenSearch. But you can do things like term expansion, where maybe you change that into a different term as you are ingesting it. So I could expand SSFO out into simple schema for observability, and maybe that will work well. Or, there are other strategies to mitigate that, such as like fine-tuning a model, which is taking a model and then retraining it on your same data set. Then the other reason that someone might not want to use vector search is because maybe it's a big cost. So vector search uses a lot more memory because all of the documents are stored in memory by default with HNSW in particular. So it's very memory heavy, and KNN compares all of the documents against all the other documents. So you're constantly doing almost like a full search against every single document. Now it uses some strategies under the hood, so it doesn't have to use exactly all, but yeah. So it's very memory heavy. It can be expensive to run. The ML models also add time to your ingestion. So your ingestion might take longer because it has to go through a machine learning model now, and then it has to be output. So those are a couple of the reasons why you might not want to use semantic search. But I would say try it. Do this, test it, and understand, maybe test it with a few different models, maybe test it with a few different methods, like maybe instead of weighting this such that the lexical search is weighted at 30% and the semantic search is at 70%, play with these weights. See what you can do. And also think about how your users are using your search, right? Are they asking questions, or are they just typing in keywords that they're looking for? With that, I am David. This has been Tiffy Bits. I hope you enjoyed this. I've got all the links below. This was also available as a blog on my website, so make sure to check that out, and I will see you next time.